Hello friends, welcome to the new episode. In this episode, we are continuing with the discussion of thermodynamics. Actually, this is the third part. In this part, we are going to discuss two concepts, spontaneity and entropy. These are two related concepts, so we have to consider their relation as well. And we are also considering this entropy interpretation of the second law of thermodynamics. So this is a discussion on second law of thermodynamics actually. Right. And also we have to consider the mathematical aspects of entropy, because entropy is a measurable property, the macroscopic measurable property. So the mathematical equations relating entropy and second law also we have to take into consideration. Right, these are the things we are going to discuss in this episode. First, we can come to spontaneous processes and spontaneity. Processes which can proceed or which have natural tendency to proceed without the aid of an external agency is what you call a spontaneous process. But of course, spontaneity has to be defined within a certain set of conditions. Then only it will be meaningful, right? We have to specify temperature, pressure, composition, etc. of a system to identify whether a process is spontaneous or not. Then only it will become meaningful, right? Certain processes which are spontaneous under a given set of conditions may not be spontaneous at other conditions, other set of conditions. That is it. Water falling from uphill to downhill is a spontaneous process, but the reverse, it can occur on its own. But the reverse, what's the reverse? Water climbing uphill is non-spontaneous. We require a water pump or something like that to do that. Okay, another case. We have two vessels, two bulbs connected by a connecting tube and a valve or a stopper. One of the bulb contain a gas, the colored bulb contain a gas at 1 atmosphere pressure, and if you open the stopper now, the gas will flow to the other bulb A, and that flow continues apparently till both the bulbs have gas in both the bulbs have equal pressure, right? So now the gas is equally distributed between the two bulbs. That happened. But the reverse of it, what is the reverse of it? Gas molecules going from one bulb to other, coming back. That is not prevented by Newton's laws of motion. But if all the molecules come back and gas molecules assembling in one of the bulbs, that doesn't happen spontaneously. That is non-spontaneous. See, instead of a gas in one bulb and the other gas empty, we can consider another situation. We have two gases in the two bulbs under equal pressure, right? If there is a pressure difference, flow will happen, that we know. Now you consider both the gases have equal pressure as well, 1 atmosphere pressure as well. Now you remove the stopper or open the valve, what will happen? The gases will mix up each other and the two bulbs after some time will have a uniform mixture of the two gases, right? Now, if you wait for a long time, the reverse will not happen. What is the reverse? The gas molecules spontaneously separating into two different bulbs will not happen spontaneously. Separation of gases is not spontaneous, but mixing up of gases is spontaneous. Rusting of an iron nail in an open atmosphere. Atmosphere will have oxygen and some moisture, we know. And the temperature and moisture, content of moisture changes, or some other factor like salinity changes, the rate of rusting will be different. That factor we are not taking into consideration. Such factors we are not taking into consideration. But we know rusting of iron is a spontaneous process. But the reverse, a rusted iron nail spontaneously getting converted. Iron nail, we have a coating of iron oxide. Ferric oxide will actually be there, and conversion of this ferric oxide back into iron will be a non-spontaneous process under that given set of conditions. You can convert ferric oxide to iron, but that require a different set of conditions, different set of experimental conditions. That is it. Melting of ice, that we know it is spontaneous above 0 degrees Celsius. And below 0 degrees Celsius, melting of ice is non-spontaneous, we see. But the reverse of that process, what is the reverse of that process? Freezing of water will be a spontaneous process. So we can see that when condition changes, spontaneity also will be different. The reverse becomes spontaneous. We can see that spontaneous process may be fast or slow. Already we have seen there are certain ionic reactions, just like mixing of silver nitrate and sodium chloride. Their silver chloride is precipitated instantaneously. That is a spontaneous process happening at a fast rate. Then explosive reactions happens at very fast rate. That is it. Rusting of iron is slow. So we can see that kinetics governs the speed of a process, while thermodynamics, principles of thermodynamics governs whether a process is spontaneous or not. That is it. If thermodynamics permits a process, the process can occur. At what speed it will occur depends on kinetic factors. If thermodynamics do not permit a process, that cannot happen. That is it. Maybe the reverse of that process will be spontaneous under such a set of conditions. That is it. And we can see this bulb filled with hydrogen, and if you bring a burning candle near it or give a spark, what will happen? The balloon will explode and the gas inside get combusted and you get water vapor as a result. Burning of the gases will happen. Hydrogen combines with atmospheric oxygen in the burning process. It's an exothermic process as well. It occurs fast. But we can see that if you keep the balloon for a long time in the atmosphere, no change will happen. Even we can mix hydrogen and oxygen and keep it in a vessel for a long time. Apparently, no change will be happening. So that is kinetics. And even though the process is spontaneous, at room temperature and the normal pressure conditions itself, the process is not actually happening or apparently not happening because of kinetic parameters. We say it is kinetically locked up. But when you give an initiation, a spark is given, then the process happens continuously. So that is it. It requires, we say, some activation energy. Initially you give some activation energy, then further the reaction is exothermic, so the reaction will continue. That's how we explain or we approach it in kinetics. That is an area of kinetics. But we can say that hydrogen and oxygen is less stable, thermodynamically less stable than water at room temperature and normal pressure. So we expect hydrogen and oxygen to combine to give us water according to principles of thermodynamics. And according to principles of thermodynamics, we see that the process is exothermic as well. But if you mix hydrogen and oxygen together, apparently no change will happen for a long time. That is another question. Okay, now we come to another concept called reversibility, because it is related to what you call spontaneity. That's why we are taking into consideration reversible processes. In a reversible process, system changes in such a way that system and surroundings can be put back in their original state. The thing is that some change is happening to the system and surroundings, and if the process is reversible, when you reverse the process, or you can reverse the process in a suitable manner so that there is no net change in system and surroundings taken together. All the changes which has happened in one direction should be reversed in the backward direction also. This is different from a cyclic process. You can bring back a system to the original state, but the system has come back to the original state, but some permanent change may happen to the surroundings in a cyclic process. That's different. A cyclic process can be reversible. That is another question, another thing. So reversible process and cyclic process are different. A reversible process, when it is reversed, there should not be any permanent change in system as well as surroundings. That is the thermodynamic condition for that. All the changes happening in one direction should go back in the other direction. And such processes can happen when the driving force for the process is infinitesimally greater than the opposing force. That's how we see. So that this process is happening by infinitesimally small steps. Right? At any stage of the process, we can consider the process is at quasi-equilibrium. Or we can consider that this is happening by a series of equilibrium steps. So this is only an idealized process. This is only a theoretical process. Thermodynamic reversibility or thermodynamic reversibility is a theoretically defined thing. All processes happening in nature will not be reversible, but they will be irreversible in nature. That is it. So you consider heat flowing from system to surroundings or the reverse. So when the temperature of the system is slightly greater than that of the surroundings, heat will flow very slowly, right? And the reverse of it is also true. When the temperature of the system is slightly slow than, by a infinitesimally small quantity, heat will flow from surroundings to the system without apparent change in temperature. Such a process is what you call reversible process. We can consider the expansion of a gas. A reversible expansion is such a case where the pressure of the gas inside the cylindrical vessel is provided with a movable piston, and such conditions are maintained. Okay. Now the external pressure is slightly less than, infinitesimally less than the internal pressure. Gas will expand slowly. And if you want to continue to expand the gas, what we have to do? So after infinitesimal expansion, the internal pressure also becomes equal to the external pressure. Sorry. And we have to go on decreasing infinitesimally slowly the external pressure. Then only a reversible expansion of the gas will take place. That is it. If there is a measurable difference between internal and external pressure, the expansion will not be slow, and the expansion will be irreversible in nature. Or if a gas expanding into vacuum also, then it will be irreversible in nature. Irreversible process that cannot be underdone by exactly reversing the change in the system. Changes in the system we can reverse, but changes in the surroundings sometimes we cannot reverse. Such processes are irreversible in nature. We can consider the expansion of gas into vacuum. So the system does no work when it is expanding into vacuum. That is an irreversible process. We say a spontaneous process as well. And if you bring back to the system to the original state, we want to compress the system. Without doing work, the system cannot be compressed. So in expansion, no work was done. But in compression, we have to do work. So the process expansion into vacuum cannot be exactly reversed. That is an irreversible process. All real processes are irreversible. So spontaneous processes are thermodynamically irreversible. That is it. And equilibrium processes, as a process at equilibrium means it is thermodynamically reversible. We can see that spontaneous processes, large number of spontaneous processes are exothermic, just like burning of any fuel or any reaction, chemical reaction. There are large number of chemical reactions which are exothermic in nature. Combination of hydrogen and chlorine, nitrogen and hydrogen, etc. are examples of what you call exothermic reaction. Methane gas burns spontaneously and is exothermic. But we can see that endothermic processes, ice melts spontaneously above 0 degrees Celsius. That is an endothermic process that is happening spontaneously. So releasing heat or releasing energy is not a sufficient condition, or not a, in some cases, not a necessary condition for a process to be spontaneous. That we can see crystallization of a substance from its solution, from its saturated solution, happens spontaneously. From a saturated solution or a supersaturated solution, spontaneously crystallization can take place. And what about the process? The process may be endothermic in nature. It may be released. Usually heat is released, right? Mixing up of gases you can consider, that we have examined earlier. That is not exothermic or endothermic. No heat is liberated or absorbed in the process, but it happens spontaneously. So there should be some other property which also has a role to play in spontaneity of a process, other than the exchange of energy. We know systems usually have tendency to go from high energy state to low energy state. That we already know from experience, and we have large number of processes which are exothermic in nature or which releases energy during natural spontaneous processes. But that is not the only criterion for spontaneity. There should be some other parameter or some other criterion also for spontaneity. There should be another measurable quantity. And that quantity is what we call entropy. And we can introduce the concept of entropy using our Carnot's engine and Carnot cycle. So in Carnot cycle, what is happening? Heat is absorbed from a higher temperature, does some work, and the excess amount of heat is liberated to a reservoir at a lower temperature or a sink. And the Carnot cycle can be represented like this. We have the isothermal expansion, adiabatic expansion, isothermal compression, and finally adiabatic compression. That is the complete Carnot cycle. So it goes from P1 V1 to P2 V2, P3 V3, P4 V4, and back to P1 V1. A gas. Gas is the working substance in Carnot's cycle. And the efficiency for Carnot cycle we have already seen in the last discussion, and that can be given as QH minus QL. H is the heat absorbed from the reservoir at higher temperature, hot, lower temperature. QL, that is the heat given out by QH, or it will be TH minus TL by TH. TH the higher temperature reservoir and TL is the lower temperature sink. Or we can rewrite it like that: QL by QH is equal to TL by TH. Or we can write QL by TL is equal to QH by TH. So if you take into account the proper sign, the expression should be minus QL by TL, because heat is given out by the system at the sink at lower temperature. That is equal to QH by TH. Now you consider the process from the first state P1 V1 to P3 V3 by two paths. Then you see that this is a reversible process, Q reversible by T. You consider the compression path, that is the second path, the compression path, also in the same direction from P1 V2 V1 to P3 V3. Then the parameters will change. We can remove that negative sign as well. If we are considering the going of the system from P1 V1 state to P3 V3 through the two paths, both the paths are reversible, right? Then we can see that the Q reversible by T is the same for the both paths. We have proven already by Carnot's cycle. So we can write as Q reversible by T is a constant, and that is the thermodynamic concept of entropy. This Q reversible by T, the reversible heat absorbed upon the temperature at which it is being absorbed. Their ratio is what we define as entropy. Okay, now we can consider, instead of Carnot cycle, you can consider any thermodynamically reversible cycle. And this can be divided into a number of Carnot cycle. One Carnot cycle is shown in the figure, and you can divide it in such a manner into Carnot cycles. And you can go on decreasing the size of this Carnot cycle. We can consider infinitesimally small Carnot cycles. Then the outer lines, what we call the adiabatic lines, will coincide with the line of the total line of the actual cycle when we are considering infinitesimally small cycle. So we can consider any reversible cycle as a sum of very large number of infinitesimally small Carnot cycles, or infinite number of infinitesimally small Carnot cycles. So what does it indicate? You can consider the dq by t term for each of the infinitesimally small Carnot cycle, and that along A to B plus that along B to A, the total should be equal to 0. Of course, it will be equal to 0. We have already shown by Carnot's theorem if you add these two together. And so we can write dq by t A to B is equal to dq by t B to A, the second path. Right. Now, if you reverse the second path, what we can write? dq by t first path A to B will be equal to dq by t second path A to B. Or in any cyclic process, dq by t, integral of dq by t terms will be 0. So what does it indicate? dq by t, the integral of dq by t along any reversible path from A to B is a constant. So that dq by t can be considered as a state function, and that is our entropy. dq reversible by t. Entropy is a term coined by Clausius in 19th century. Clausius was convinced of the significance of ratio of heat delivered and the temperature at which it is delivered. That is this is the conceptual discussion of entropy. You don't worry much about it. So this is our definition for entropy, mathematical definition. Yes, we are defining not absolute entropy here, but we are defining the thermodynamic entropy, that is given as the change in entropy here. ds is equal to dq reversible by t. We are considering an infinitesimally small process. dq reversible is the heat reversibly absorbed in that process divided by the temperature at which the process happens. And suppose the process is happening at a constant temperature, then we can write delta S is equal to q reversible by t. If the temperature is changing during the process, we cannot simply write q reversible by t, then we have to express this dq reversible as a function of temperature and then do the integration. Then only we can get delta S. That is the difference. We have ds equal dq reversible by t, that's fine. And if temperature remains constant in a reversible process, we can also write delta S is equal to q reversible by t. But in a process in which temperature changes, we cannot simply write delta S is equal to q by t. Sometimes for rough approximations, you take the average temperature and divide by q by t. That is only a rough approximation. That is not giving the actual value. If you want to get the actual value, what we have to do? We have to express this q reversible as a function of temperature, then integrate ds from temperature T1 to T2 or Ti to Tf. Then only you can get the change in entropy. Entropy can be thought as, physically, entropy can be thought as a measure of randomness of a system. So we are considering absorption of heat by a system. So we know heat is what we call the random kinetic energy. It is nothing but random kinetic energy of the particles. So when more heat is pumped into a system, what is happening? We are increasing the randomness in the system, because molecule will be jiggling more violently now. If it is a solid, still the molecules are jiggling in their mean position. If you pump in heat, it will start vibrating more vigorously. This is true for any state of the system. Pump in heat, what happens? This random movement increases, and we can consider in that way we can relate it. This is related to various modes of motion of molecules. That also we can come and explain. So we can see solid, liquid and gas. So when a solid is converted to liquid, entropy increases, because we can see that arrangement has becomes more random. When you come to gas molecules are free to move further, and we can see that there is increase in entropy from solid to liquid, liquid to gas. Similarly, when temperature increases also, entropy increases. And also we have to see that the heat absorbed is divided by the temperature at which the process is happening. There is some significance for that also. If you suppose you have a system at a low temperature and a system at a high temperature, say room temperature and at 100 degrees Celsius, and you put in the same amount of heat to both systems, the system at 100 degrees Celsius is already in a state of disorder or randomness, and putting the same amount of heat in that system will not increase the degree of randomness to the same extent as the system at a low temperature. That is the basic argument. Already it is disordered. Disordered system, to increase disorder is difficult than an ordered system. Making a ordered system disordered, or what you call making a mess of an ordered arrangement of your room, is easy. But already you have made a mess out of it, and you are asked to make more mess. You will find it difficult actually, right? Okay. Another concept regarding entropy is molecular arrangement, and actually it is concerned with the energy states of the molecules, how an energy state can be attained in number of different ways. That is the distribution of energy between the molecules. That is the modern concept of entropy, statistical concept of entropy. But we are not going into the details. But we can see that we have the colored buttons here, colored balls here, small pebbles. You can consider it as anything. Color is given just to distinguish between them for our convenience. The balls are not actually colored. Imagine like that. We want to, you can even number it 1, 2, 3, 4. For this is more easy to identify it, and the color is only for us, not for the system. Now we have 4 balls. We have 2 boxes. We have 8 positions in the boxes. 2 boxes, 4 each, and all the positions have equal probability. That you consider. You can choose any position for any ball. That is it. Any position for any ball. That's how the nature works. And all the 4 goes to one. All the 4 goes to the other. That can be attained only in one way: the topmost and the bottom. Right? 1 go to the first box and 3 goes to the second box. That can be attained in 4 different ways. Right? The reverse also is true. Now you consider 2 balls or 2 pebbles in each of the box. Right? You can change the position and the balls. So what happens? 1, 2, 3, 4, 5, 6. 6 ways in which they can be arranged. Don't worry about the color. If color is also taken into consideration, there will be other permutations also will be there. Color is for us only, not for the system, right? To distinguish only. So you can see that this arrangement can be attained in more number of ways. 2 balls. For us, we are not concerned about which position inside the box these balls occupy. we are concerned the macro configuration, where how many balls are in each of the box. So 2 balls in each of the box can be attained in a number of different ways. So we say that this is more probable, or this is having more entropy than the other. That is one way of approach, and we are not going into details. So entropy is related to the molecular arrangement also. Number of ways in which a particular macro configuration can be attained. That is entropy according to statistical interpretation, Boltzmann's interpretation. We are not going into that details here. Just for a sake of information, that slide is included here. And we can see that entropy is a state function. We have already proven that. That is a constant. It depends on initial and final state, not by the path by which the process happens. So that is a state function. Change in entropy can be given as delta S is equal to S in final minus S initial. Whatever the path through which the process is happening, if it goes to the final state, the change in entropy will be the same. And it is defined as the integral of Q reversible by T, dQ reversible by T. Now you consider a reversible and irreversible process. System goes from state 1 to state 2. Delta S is Q by T, reversible, Q reversible by T. Suppose temperature is the same. We are considering an isothermal process. Okay, if it is not an isothermal process, we will have to integrate it. That's all. dQ by T, reversible. You integrate that, you will get. That's fine. And we have to see that the same change we are doing by another path which is irreversible in nature. But change in entropy, delta S has to remain Q reversible by T. That is an important conclusion from the above discussion. Whether the process is reversible or irreversible, we need not worry about it. The change in entropy has to be obtained as Q reversible by T, always. That is it. Process may be irreversible, but the mathematical parameter you have to bring in to calculate the change in entropy, to find out, to determine the change in entropy, will be Q reversible by T. We can consider the Carnot's engine and the hot reservoir together. The reversible isothermal expansion that is happening at the hot reservoir. Then the change in entropy for the system is QH by TH, and for the which part, the reservoir is minus, because it is losing heat, minus QH by TH. So the delta S total is 0. So that in the reversible process, we can see that the system and its immediate surroundings taken together, the change in entropy is 0. System and surroundings taken together, the change in entropy will be 0 in a reversible process. Okay, that is it. Delta S total is equal to delta S system plus delta S surroundings. And the process is reversible. We can write Q reversible by T for the system, and for surroundings it will be losing of heat. So there is decrease in entropy in the surroundings if it is absorbed by the system. So it will be minus Q reversible by T, and that will be equal to 0, a reversible process. And that is applicable for equilibrium as well, that we know. For equilibrium, delta S total will be equal to 0. And if it is an irreversible process, so in the slide, the second step, we have to correct it as irreversible. It is by mistake, it is put as reversible process itself. So if it is an irreversible process, we can see that the change in entropy of the system will be the same. It will be Q reversible by T itself, because change in entropy depends on initial and final state only. It is a state function. We have already proven it. Right. Now, what about the surroundings? You consider the vast surroundings outside. As far as the vast surroundings outside, the rest of the universe is taken as the surroundings. When we take the rest of the universe as the surroundings, the change happening can be considered as an infinitesimally small change. If it is an infinitesimally small change, it can be considered, the process can be considered reversible with respect to the surroundings. That is the type of argument put forward for this entropy law or the second law of thermodynamics. So, in the second case, the process is irreversible. Change in entropy of the system remains the same as the above case, but surroundings, we can consider this irreversible process are reversible as far as the vast surroundings are concerned. So, we can take the change in entropy of the surrounding as minus q irreversible by T, right? And we know that the heat exchanged in a reversible process is always greater than heat exchanged in irreversible process. So, what does it indicate? Q reversible by T minus Q irreversible by T, and that will be greater than 0. So, in an irreversible process, change in entropy, total change in entropy, entropy of the system and surroundings taken together is greater than 0. This is our second law of thermodynamics, actually. You can't break even. According to first law, we can break even. We can only break even, but we cannot break even as well, because always there will be an increase in entropy in the surroundings in spontaneous processes. Entropy increases means surroundings will have lower capacity to do work. That is another thing. We leave it now. So, delta S universe, that is delta S total, is equal to delta S system plus delta S surroundings. That is equal to 0 for ideal reversible processes or processes at equilibrium. And irreversible processes, they are real, spontaneous, this sum, the total and change in entropy will be greater than 0. The second law statement can be given like this: in any spontaneous process, there is always an increase in the entropy of the universe. The entropy of the universe is increasing. All these are statements of second law. For a given change to be spontaneous, delta S universe must be positive. Okay. What we call positional entropy, where we have ordered arrangement of particle. If it goes to disordered arrangement, we have what we call entropy increases. We say microstates and macrostate, that I have given an earlier picture. Entropy is related to temperature. I have already discussed it. Delta S universe is equal to delta S system plus surroundings. Entropy changes in the surroundings are primarily determined by heat flow, right? The magnitude of entropy is dependent on temperature also. The lower the temperature, the higher impact to the surroundings of the transfer of energy. Energy is transferred from the system to surroundings if we are considering. If the surroundings is at lower temperature, the higher will be impact of the transfer of heat. That is true for any system also. We are pumping heat into a system. We are pumping heat at a lower temperature and we are pumping heat at a higher temperature into a system. You consider it need not be pumping, heat flow from the surroundings to a system, right? At a lower temperature, it will make more impact on the molecular arrangement than that at a higher temperature. That is it. So, entropy is proportional to heat transferred and it is inversely proportional to temperature at which heat is transferred. Now, we can consider exothermic processes. Exothermic processes means heat is liberated. It is given out to the surroundings. So, surroundings entropy will be increasing. Delta S surroundings will be positive. In endothermic process, delta S surroundings will be negative. Okay. Now we come to what we call a mathematical statement of the second law. Closures inequality, sometimes it is put as. We know the definition for entropy is ds equals dq reversible by T. And now, suppose the same process is happening irreversibly. We are considering the system alone. Change has happened irreversibly. then we can see that dq reversible is always greater than dq irreversible. Work done or heat exchanged in a reversible process is always greater than that in an irreversible process. That is it. So for an irreversible or spontaneous process, as far as the system is concerned, ds will be greater than dq irreversible by t. That is it. We can combine these two together. That is the statement of second law, sometimes called Closures inequality. Now, if you put the first law equation, what is the first law equation? du equals dq minus pdv, or dq is equal to, we can write du plus pdv. So we can write ds is equal to or greater than du plus pdv by t. That is the Closure statement for second law of thermodynamics. Equal to sign refers to equilibrium or reversibility, and greater than sign refers to irreversibility or spontaneity. Now we can come to what you call change in entropy. Okay. Change in entropy is given by our thermodynamic definition. What is it? ds is equal to dq reversible by t. Now you put the first law equation into it. du equals dq reversible minus pdv, where minus pdv stands for the work done. Only work done is expansion type. That is our consideration. Then we can write ds is equal to du plus pdv by t. And we know du plus pdv, if pressure remains constant, it is equal to dh. We can also write ds is equal to dh by t. If we are considering a process taking place at constant temperature and pressure, the equation becomes delta S is equal to delta H by T. For constant pressure temperature processes, delta S is equal to delta H by T. Phase transitions we can consider. It can be put as delta S is equal to delta H by T for any phase transition. If it is vaporization, you consider the vaporization process that is happening at its normal boiling point. At normal boiling point, a liquid and gas can be in equilibrium with each other. Right. Then you can write delta S V equals delta H V by T. It can be any equilibrium of the liquid and gas other than the normal boiling point also. We can apply the expression. Then the pressure will be different. That's all. When you change the pressure, what happens? The temperature also will be different. That's another thing. Similarly, for fusion process also, Tm, there is the normal melting point. Delta SF is equal to delta HF by Tm. Similarly, you can have another equation for sublimation or for any phase transition. Okay, now we are considering change in entropy for ideal gases. Our equation for change in entropy is ds equals du plus pdv by T. Already the first law is applied there. Now for an ideal gas, we know Cv is equal to dou u by dou Tv, or we can write du is equal to Cv dt. And if you put that, ds is equal to Cv dt plus pdv by T. If we are considering 1 mole of a gas, Pv equals RT is substituted, what we get is ds is equal to Cv dt by T plus P into dv by V. Simply putting Pv equals RT. Okay. For n moles of an ideal gas, we will have to multiply by n, ncv dt by T, nr dv by. Now you can do the integration to find change in entropy. ds S1 to S2. Right. Cv dt by T, T1 Ti to Tf, r dv by v integral vi to vf. And if you do the integration, it will be Cv log Tf by Ti plus R log Vf by Vi. For n moles, you multiply it by n. That's it. And we can make expression in terms of Cp as well. We know Cp minus Cv equals R and V is equal to RT by P. We put the substitutions in this expression, the integrated expression itself. We can easily simplify to Cp log Tf by Tf minus R log Pf by Pi. That is only change. Cv is substituted by Cp, then we have R log Pf by Pi, but the sign changes from plus to minus. If you substitute it and do the mathematical steps, you can easily see this. So these two expressions you should be familiar. And we consider different types of processes, isothermal processes. If you consider isothermal processes, what happens? The first term, both for Cp and Cv terms, vanishes. So what will be remaining? It will be R log Vf by Vi or minus R log Pf by Pi. That will give you the change in entropy during isothermal expansion or compression. If we know the initial volume and final volume or initial pressure and final pressure, we can find it out. That is it. That's for 1 mole of a gas. For n moles, of course, multiplied by n. Constant volume processes, what happens? The second term in the Cv equation vanishes because log 1 is equal to 0. So what we will get? Delta S is equal to Cv log Tf by Ti. If it is a constant pressure process, you can take expression in terms of Cp and the second term vanishes there. Then we get delta S is equal to Cp log Tf by Ti. Okay, that about the mathematical steps involved, mathematical equations involved for change in entropy. So now I hope that we have just gone through the concept of entropy, spontaneity and reversibility and how it is related to second law. So second law have different statement in terms of the work, conversion of heat into work and what we call change in entropy. And we can see that in cyclic processes, some heat is always given out to the surroundings. That is increasing the entropy of the surrounding. So there also you can see that entropy is increasing. Entropy of the universe is actually increasing in when you obtain continuously work from a source. In a entropy of the surroundings is increasing. We can see that entropy of the surroundings in such a each cycle will be increasing. That is it. And we know in all spontaneous irreversible processes, entropy is increasing. The nature goes from a ordered state to disordered state. That's happening everywhere. But we can have discussion based on whether a highly ordered, complex living things grow and flourish in nature. Is it against the second law of thermodynamics? Not actually against second law of thermodynamics. You can have processes in which this entropy decreases locally, but entropy will be increasing elsewhere. So they will be coupled. A process in which entropy decreases locally, but increases elsewhere. These two processes will be coupled, then it will become spontaneous. That is happening. And that concept we can discuss later, including the new parameter called free energy as well. That is in the other part. Okay, thank you. Thank you. Bye. See you.